Hello and welcome back to ECE 44. This is lecture 29 of fall 2021. This lecture is being pre-recorded. It is not a live recording, so let's continue. Okay, last class, what did we do? We talked about computing the step invariant transformation using Laplace and Z transforms. Now remember, we're going to be doing direct design. We're going to be designing controllers in discrete time. And when we do that, we want to discretize the plant, and we will always use the step invariant transforms, i.e. C to D, to discretize the plant. We will not use any other method for discretizing plants. And the reason for this is because when we use the step invariant transformation, we get exactly the behavior of the system at the sample points. No approximations. Okay, so we've now learned how to compute the C to D in both state space and transform domains. And again, that's feasible for small problems. For larger problems, of course, you'll use MATLAB. Okay, and we started talking about some of the properties of sampling. In particular, we talked about, or the effects of sampling. In particular, we talked about pathological sampling. Okay, and this is something we want to avoid because it can cause the discretized plant to not capture some of the behaviors of the continuous time plant. Essentially, it's like aliasing, but at a system level. Okay, and most sampling frequencies that you pick or sampling periods won't result in pathological sampling, but we should be aware of it, right? It's something that can happen. Okay, so the last aspect of the effect of sampling we want to talk about is the frequency response. What happens to the frequency response of our discretized plant? Okay, and so we're going to consider this setup here for this discussion. Okay, so let's kind of go through it, what's in this picture. So we're going to have an input u in the continuous time domain, which is going to be applied to a continuous time plant P of S. Okay? And we're going to assume that this plant is Bibo stable. Okay? And what we'll apply, the type of input we're going to apply is a sinusoidal input. So we're going to apply cos omega t. And we want to see what happens in steady state. Now in steady state on the top branch here, because we have Bibo stability, we know that we will get in steady state a sinusoid of the same frequency, omega, with a possibly different amplitude and a possibly different phase. Okay, we've seen this many times, but I'll write it out. So in steady state, what we will get is the following. Okay. And the change in the amplitude and the change in the phase depends on, of course, the plant model, the model of the continuous time system. Okay, on the bottom branch, in the purple box, we have the step invariant transformation of the same P of S, the same plant. Okay, and of course this is P sub D of Z, which we call C to D. And what we saw last class, when we were discussing eigenvalues, or a couple of classes ago maybe, is that if the continuous time system is Bibo stable, then the discretized system will also be Bibo stable. So we know this guy down here is also going to be Bibo stable because C to D preserves stability. All right? Okay, so what is the steady state output of this bottom branch going to be? Well, to be able to compare them, first thing we need to do is we need to sample cos omega t. We can't apply a continuous time signal to a discrete time plant, so we'll have the signal here, after the sampler, is going to be cos omega. And now I replace the time variable, continuous time variable t, with the sampling instant, which for us, I'm going to write it as t times k. Okay. And if you think back to what we did in chapter 6, okay, so I remind you here, this here is the input frequency. This is the sampling period. And if you think back to what we did in chapter 6, when we were doing the frequency response of discrete time systems, we would just call that symbol, it was multiplying k, we just called it theta. So I'm going to do that same, use the same convention here. So we're going to define theta to be omega times t, right? It has the right units of radians. Okay, so again, back to chapter 6, what we know is that the output of this top branch, or the bottom branch then, is going to also be a sinusoid discrete time sinusoid of frequency, if you will, theta, with a possibly different amplitude and a possibly different phase. And it looks, roughly similar, but we end up with the following. All right, and we want to know basically how similar are these responses, right? Because we're going to, if we want to design a system to track, say, it's things at a certain frequency, we want to know, how our discretization behaves at those frequencies. And so the question we want to briefly, it's going to be a very quick discussion, is to understand what is the relationship between the continuous time frequency response and the frequency response of its discretization. And of course, this is relevant for design in the frequency domain. So by that I mean things like lead, lag, etc. Okay? So this is what we want to understand. Like, when is it that the discretized system behaves roughly like the original continuous time system? And when does it start to deviate? Okay. So let's do exactly what we did in chapter 6. Let's write theta as a piece in the baseband between negative pi and pi, and then plus an integer multiple of 2 pi. So as in chapter 6, in particular section 6.8, write theta equal to theta naught plus 2 pi n, where n is an integer, and theta naught belongs to that region, right? So it's that component of theta, in other words, the theta naught component, which determines the response of the discrete time system. Everything else, everything outside of that range, everything corresponding to this, has no effect, right? Essentially, it's like aliasing. Okay, so there's that. And what about in terms of the original omega? In terms of omega, what is that decomposition into a baseband and a non-baseband? In terms of omega, we have that theta equals omega t, which equals some baseband component, omega naught over t, plus 2 pi n. Right? So this guy here is theta dot, right? So this guy belongs to negative pi. And so if we think of this in terms of omega naught, we see that omega naught should be between negative pi over t and pi over t. Right? And this is our baseband. Okay? So if you think now back to our picture, as soon as the input frequency, omega, is outside of the baseband, in some sense, the input going to the continuous time plant becomes vastly different than the input going to the discrete time plant, right? The input itself is now different because of aliasing, okay? And so there's sort of a limited range of frequencies where this lower system can even, respond to. At a certain point, it just can't respond to higher frequencies because you get aliasing. And that highest frequency it can even possibly respond to corresponds to this baseband. And so we see that the inputs, forget about the response, that the inputs themselves to the top and bottom branch are similar if omega is in the baseband. In particular, is sufficiently within the baseband. Right? In other words, omega equals omega naught. There isn't this extra bit. Right? So the input themselves will be similar, and if the inputs are similar, then we would expect the responses to be similar, and that is the case. And so it turns out that we will conclude the P of j omega is approximately equal to P sub d e to the j theta if the input frequency, the omega, is sufficiently inside the baseband. And so I'm going to write this as that, pi over t. Now, what is pi over t? Well, of course, that's just the sampling frequency divided by 2, which of course equals the Nyquist frequency. Okay? So what we're saying is that we expect the frequency response of the discrete time system to appear like that of the original continuous time system as long as the frequencies that you're applying to it are sufficiently small. What does much, much smaller mean? The rule of thumb is that omega should be less than or equal to 1/5 the Nyquist frequency. Okay. And you should take a look at examples 743 and 744 of the notes. Okay, so, and I also want to show you this example, 742, quickly. So here we have a continuous time plant P of S. Here we have its discretization, and the sampling frequency is 10 radians per second. Okay, so let me highlight that. Okay, and what you see below is the Bode plots for these two systems over the range from 0 up to the Nyquist frequency, so up to pi. So this goes from 0, well, it's a log scale, so 0 is over here, and this point here is pi over t, which equals 5 rads per second. Okay, oops. Right. And so again, what you see from this diagram is what the conclusion we drew above. For small frequencies, the responses are sort of indistinguishable. Okay? As you start to get closer and closer to the Nyquist frequency, you see that there's this deviation. They start to change. In fact, you already see it here. Okay? And so that's what we're saying, that the frequency response is going to be similar. And so again, if your control loop is going to be, tracking signals of, say, 60 hertz, right? Say you're doing a power application. You want to make sure you sample fast enough so that the Nyquist frequency is well above 60 hertz, because that's, our rule of thumb is 5 times above 60 hertz, right? So this is just another way to think about conditions for choosing the sampling period. Okay. If you're interested, there's an appendix in this chapter which derives an exact relationship. So, if interested, you won't be tested on this. This is purely out of interest. Appendix 7b derives the exact relationship between the continuous time frequency response and its discretization. Okay, so that's it for chapter 7. It was a brief chapter. And again, what did we learn in that chapter? We learned how to discretize plants and some of the effects of sampling. What happens to stability, eigenvalues, what happens to pathological sampling, so system type aliasing, and frequency response. Okay, and now we're going to go and do our design. Okay, so here we go, chapter 8. All right, so here we go. Chapter 8. Control design in discrete time. Part 1. And so here we'll use transfer functions. Okay. And then we'll do time domain, time permitting, in chapter 9. Okay, so the picture is the usual. Okay, we have our sample data set up, where we've moved the sampler from, instead of modeling it over the input of the plant, we've just moved it to the output, or input of the controller, we've moved it to the output of the plant, and no approximations are being made, right? So this is, we're going to view this as a discrete time system. We're going to take the point of view of the computer in our very first introductory example way back in the first week. So as always, this here is our plant. So this is P sub D. Okay. And we're going to treat this, even though it's a sample data system, we are going to essentially ignore the inter-sample behavior. So between samples, the plant is doing stuff, we're going to ignore that, right? That we're going to treat this as a discrete time system. And if we don't have pathological sampling, that's probably going to work out pretty well. And of course, we will avoid pathological sampling. Okay, so in terms of notation, I'm going to drop the D. So notation, we're going to drop, I'll drop the subscript D. And I'm going to write P of Z for the plant, right? Because again, we're going to treat this as a discrete time system. So for us, at this point, it doesn't actually matter if the discrete time plant arises from discretizing a continuous time system or whether it is naturally modeled as a discrete time system, okay? When it comes to intersample behavior, it's best addressed through simulation, right? So simulate your sample data system and see how it's behaving between samples. Okay, so we move on to the first section. And this is going to be, you can think of this as exam prep. It's like a review. It's going to be a review of stuff we've already seen. This is pole placement using polynomials. Okay, we've seen pole placement in chapter 3 for continuous time systems. Hopefully you remember the idea there. The idea is that we turn our specs into desirable pole locations, and then we design our controller so that the closed loop system's characteristic polynomial has roots in that kind of good region. Okay, that's what we did in continuous time. In discrete time, it's going to be almost exactly the same. So pole placement in discrete time is almost exactly the same as in continuous time. Okay, so I'm going to go relatively quickly. I'm not going to spend as much time in this section as I did in continuous time because we've seen this. It's going to be very familiar to you, and I apologize if it's too familiar. Okay, so we're going to write for our plant. I'm going to write it as the numerator of the plant over the denominator of the plant. Okay, rational. Okay. And then I'm going to write these two polynomials. Let me write them out, and then I'm going to make a comment about the notation. Okay, and these coefficients, of course, are real numbers. Okay, I just want to make a small comment here about the notation. The convention of the subscripts, in other words, the numbering of the subscripts of the A's and B's, is following the convention from chapter 6 on discrete time systems. Right? So in discrete time systems, this is the way we wrote the coefficients, which is fine. But I want to point out that that's a slightly different convention that we used for continuous time systems. Okay, so just keep that in mind. All right, so that, in other words, in continuous time, we would have called this A sub n minus 1 as opposed to A1. But otherwise, it's the same thing except we're using Z's instead of S's. Okay. If we remember from chapter 3, if we have an nth order plant and we want to solve a pole placement problem, we would pick a controller whose order is 1 less than the plant, so order n minus 1. So we're going to do the same thing in discrete time. So the plant is nth order. So, as in chapter 3, we pick an n minus 1th order controller. Okay, now let me write down the controller. Okay, numerator of the controller denominator of the controller. Okay, so yes, we do use D for the discretized or the digital control law, but I don't want to use D in the subscript here. I want to use C for controller. Also for symmetry with respect to chapter 3. Okay, so there's our controller, and we're going to write this as the same way. Okay, real rational controller. Now, if we're doing pole placement in continuous time and we had an nth order plant and an n minus 1th order controller, then we would get a characteristic polynomial, which is order 2n minus 1. So the characteristic polynomial of this system, as we saw in chapter 6. And when I say this system, of course, I mean this discrete time system up here, right? Where again, we are now ignoring this intrasample behavior. We are treating this as a discrete time system. And so we can use our ideas from chapter 6. And we remember that it has the same form as continuous time. So characteristic polynomial is denominator of the plant, denominator of the controller, plus numerator of the plant, numerator of the controller. Okay, so formally exactly the same as continuous time, except that we have Z's instead of S's. Okay, and the degree of this guy is less than or equal to 2n minus 1, and of course it depends on the actual degree of the controller. Some of the F's and the G's could be 0. Okay. So what do we do in this case? If we want to define a desired characteristic polynomial, we need to pick some desired closed loop poles, i.e. roots of the characteristic polynomial. And here's the part where we start to differ from continuous time. It's not clear at this point, and I admit that, and we'll circle back around to this. It's not clear, how do I choose pole locations for a discrete time system? Right? And we have these ideas from chapter 3 for continuous time systems, but we don't have something like that for discrete time systems. So this step, admittedly, is not yet clear how we're going to do it. But for now, let's say we know, and we choose 2n minus 1 desired, in quotes, closed loop poles. And of course, when I say closed loop poles, I mean roots of the characteristic polynomial. Okay. Inside some good region, let's call it d sub g, of the z-plane. Okay. At the very least, we're going to want closed loop stability, so our good region will always be inside the unit disk. Will always be a subset of the open unit disk to ensure stability. Okay, but again, it's not clear how we do that, but let's say that we were able to choose them. Okay, so the desired poles okay, I need to choose 2n minus 1 of them. In continuous time, we use the symbol lambda. In discrete time, I'm going to use the symbol xi. Oops. So xi1. The desired poles define or generate a desired characteristic polynomial. Okay. By same way as continuous time, we're going to get this desired characteristic polynomial. And pi desired of z is going to be the polynomial whose roots are these locations that we've picked. Okay, so that looks, again, very much like continuous time, except we're using z instead of s. Okay, multiply this out. And we get some polynomial in z. Okay, and the alphas, of course, those coefficients are real numbers because we've picked the zetas, these guys, to have symmetry, conjugate symmetry about the imaginary axis. Okay, so we end up with real coefficients. Okay, so in other words, this problem looks exactly the same as continuous time. This is the same problem we saw in continuous time. Namely, given polynomials, right? Two of them coming from the plant. Oops. Given the polynomials which define the plant, and given the desired characteristic polynomial, find the controller, which is, dc nc, such that the actual characteristic polynomial equals the desired characteristic polynomial. Literally exactly the same. There is no difference in the problem. The only thing that is going to be a little bit different is how we pick the desired pole locations, but everything else is exactly the same. Okay. And so as a result, the design equations in discrete time are exactly the same. as in continuous time. For the vanilla pole placement or pole placement with a strictly proper controller. For those two cases, it's exactly the same. Okay. Let's look at the case of second order plant, right? In the case of a second order plant. For a second order plant, we get the following equation. Okay, and the structure is going to be very similar, or exactly the same, really. So here are our controller gains. Okay, again, because of the way I've written this, the transfer functions, the subscripts of the coefficients are slightly different, but the meanings are the same, right? In other words, which term, they are the unknown controller gains. The right-hand side depends on the desired characteristic polynomial. So in this case, it would just be like this, right? Second order plant. So it depends on desired car poly, or in other words, desired pole locations. And then this guy here, the matrix, the 4x4 matrix, depends on the plant information. And we construct it, or we build it in exactly the same way. The first column comes from the denominator, where we list the coefficients of the polynomial in the denominator from the highest power to the lowest power. So in this case, right, and when we run out of information, we just pad with zeros. We shift, and as soon as we hit the bottom, we stop. All right? And then we do the same thing using the numerator coefficient. So in this case, it would be B0, B1, B2, 0. And we shift again. Okay? And I'll make the same comment I made in continuous time. This has a nice structure. It depends on the plant only. Okay. So everything is similar to continuous time. Okay. And this equation will have a unique solution if and only if the plant numerator and the plant denominator do not have any common roots. Okay. Which, of course, if you're dealing with a transfer function, you will always see it that way. You'll always get it in reduced form. The only time that might be relevant is if you generate the denominator and the polynomial separately using state space methods. Then, of course, they might not be coprime, but if you're given a transfer function, it will be coprime for the most part. Okay. All of the caveats that we have made in continuous time and that you've seen in the labs apply in discrete time as well. So let me write it down to be extremely explicit. So just as in continuous time, pole placement doesn't tell us about the closed loop zeros. Right, we are focusing on placing the roots of the characteristic polynomial to the detriment of the zeros. Okay, and so as a result, we do not know what is happening in the frequency domain. So we don't know what is happening in the frequency domain. Okay. So the final controller, or the final design, may have poor stability margins or sensitivity. Right? Sensitivity to parameter changes in the plant. Okay? And so the advice, just like in continuous time, is that after you've done your design, just draw the Bode plots. Draw the Bode plots and take a look at them. Make sure that they seem reasonable to you. Okay? So after designing D of Z, we should check the Bode plot, or Nyquist if you prefer. Of the loop gain, which in this case will be the controller times the plant. Right, that's the loop gain. To get a handle on what is happening in the frequency domain. You know, check the bandwidth, check the gain margins, check the phase margin, check the stability margin. Okay, check all those things, because it might help you differentiate between different designs. Okay, so in some sense this was a review, right? We just basically covered stuff you've already seen, right? We're basically using Z's instead of S's, but nothing really is new. But there was one issue that was not clear. And that is the question of how do we pick the pole locations in discrete time? We said that somehow we were picking them. We know they should be in the unit disk, but other than that, how do we pick them? So let's deal with that. Picking desired Z-plane pole locations. Okay, and here we're going to rely on some of the knowledge that we learned in chapter 7. Right? We know what the step invariant transformation, the C to D operation, does to poles. So in chapter 7, we have seen that the step invariant transform C to D maps continuous time poles at S equal to lambda to discrete time poles at Z equal to E to the lambda t, where t is the sampling period. Right? This is what we've seen. So let's use that knowledge. Let's use the knowledge we have from chapter 3 on how to pick good S-plane pole locations, and then use the fact that we know how they get mapped over when we do C to D. So the idea here is to define CG in the S-plane the same way we did in chapter 3. In other words, use your settling time spec, your overshoot spec, your phase margin spec, generate a good region in the S-plane, same exact way. And then take that good region in the S-plane and map it over to the Z-plane. Then C to D maps CG to DG. Which are the set of Z, where Z is equal to E to the ST, S is in CG. Okay, so that's the basic idea. And so if you had to think of this graphically, we won't ever draw DG. DG is not easy to draw, unlike CG. We've got the real part, imaginary part of S. Our typical good region would look something like this. I'm not drawing it very well, but this is what our typical good region would look like in the S-plane. We map this over to the Z-plane like so. Because it preserves stability, we know that this is going to be inside the unit circle. So let me try to draw the unit circle. Something like this. Right, so let's call this -1, 1, 1, -1. So everything's going to happen inside of the unit circle, but it's going to be within, and that region is going to look, I mean, it's not really so important, but it's going to be some blob. I'm going to draw it like this. DG. Okay, I don't actually know what it looks like, and we'll never draw it, but that's the basic idea, okay? All right, so what's the procedure? Determine CG using transient specs like maximum settling time, maximum overshoot, minimum phase margin, etc. Okay? Choose your desired pole locations in the S-plane. So choose 2n-1 desired pole locations. And let's call those lambdas. That's what we used when we did in chapter 3, right? Same symbol. In the good region. Okay? Just like before. So ensure there are 2 dominant complex conjugate poles. Okay? So in other words, the first 2 steps of our procedure are no different than what you do in continuous time. That's how you would do it in continuous time. There is an extra step though in discrete time. What we'll do is, as kind of pictured above, we'll take those desired pole locations and we'll map them to the Z-plane. So step 3 will be to generate the desired Z-plane locations. The desired Z-plane poles are these ECEs. Dot, dot, dot. Okay? And that's the procedure. All right? And that's how we will pick our desired pole locations for doing discrete time pole placement. Okay, so I'm going to stop there. The takeaway message here is that, as long as we're careful about discretizing our plant and, picking reasonably good sampling periods, we are then going to treat it like a discrete time system. And the first design method we've talked about is pole placement. And the good news, or maybe bad news, depending on your point of view, is that it's exactly the same, right? In some ways, we've reviewed Chapter 3 material. The only difference is that when you pick the pole locations, you have to use, we use this procedure here. Okay, a slight difference in the way you pick the pole locations, but the equations you solve, the structure of the controller, everything is the same. Okay? All right, that's it for today. I will see you guys next week.